Hyperbolic Geometry, a video by Sindhu and Sophia.
We'll start with a bit of math overview.
Hyperbolic geometry is an example of a non-Euclidean geometry, that is, the negation of Hilbert's axiom of parallelism holds. So, for any line L and any point P not on L, there exists at least two lines through P that are parallel to L. This is known as a non-Euclidean Hilbert plane. From Saccari's work, it is concluded that in this plane, when Aristotle's angle of unboundedness axiom holds, rectangles don't exist, as well as triangle angles add up to less than 180 degrees. In this situation, in fact, the universal non-Euclidean theorem holds, stating that there are infinitely many distinct lines through P parallel to L. Then, to make the plane hyperbolic, we further require that limiting parallel rays exist. More specifically, again for any line L and every point P not on L, a limiting parallel ray PX emanating from P exists and does not create a right angle with PQ, where PQ is perpendicular to L. This is known as a Hilbert's hyperbolic axiom of parallels. It follows that the parallel lines through P in a hyperbolic geometry are different from what we expect in standard construction, and it is these very differences that lead to many new interesting phenomena we're going to cover later.
A real hyperbolic plane is one where Dedekind's axiom is also satisfied. That is, for any line L, the set L of all points incident with L can be written as a disjoint union L of some 1 and some 2, which are non-empty sets of points on L such that no point of some 1 is between 2 points of some 2, and no points of some 2 is between 2 points of some 1. Then there is a point O incident with L such that some 1 is one ray on L from O, and some 2 is the opposite ray without O.
One unique phenomena of hyperbolic geometry is triangle areas. When it comes to Euclidean geometry, finding the area of a triangle was pretty intuitive, using our knowledge of rectangles. Any triangle can be split into two right triangles, where each has the area of half of a rectangle, as we know that a rectangle is always made of two congruent right triangles. However, in hyperbolic geometry, we know rectangles don't exist. We have to redefine area then. Now we see area as a positive number with invariance under congruence and additivity holding. To get a more concrete definition, though, we need to introduce delta. We define the defect delta of a triangle area to be the positive value left over when subtracting the sum of a triangle's angles from 180, as we know that in a hyperbolic geometry, the sum of a triangle's angles is less than 180 degrees. In this definition, it's proven that delta for one large triangle is equal to the sum of the delta for the smaller triangles that make it up. Therefore, additivity holds. Gauss noticed at a young age that the defect's definitions and properties match the redefined definition of area for triangles in the hyperbolic plane. He then concluded that area of a triangle, say ABC, is equal to kappa squared times the delta of ABC, where kappa is a positive constant. Therefore, in a hyperbolic geometry, the area of a triangle is at most pi kappa squared.
Another interesting thing about hyperbolic geometry is its curvature, denoted by k, where k equals 1 over Gauss's kappa constant. It is easiest to think of curvature of a geometry by considering a point on a Euclidean surface. A Euclidean plane has zero curvature. The tangent plane to the point in the case of a zero curvature intersects the surface at a line. In a spherical model, k is greater than 0, and the tangent plane at a point on the surface only touches that very point. This makes sense when you think of a sphere, as it is constantly curving away. Now, in a hyperbolic geometry, every point is a saddle point, where all orthogonal derivatives are 0, but they are not extrema. This leads to the tangent plane intersecting our surface, cutting it into two parts. This type of curvature is k less than 0, negative.
The final phenomena we will mention in this section involves the circumferences of circles in both the hyperbolic and Euclidean geometry space. For both the Euclidean and hyperbolic geometries, the circumference is given by the limit n approaches infinity of p sub n, where p is the perimeter of a regular polygon inscribed in a circle with n sides. Now, in the Euclidean case, we'll make use of the following triangle. Now, this triangle represents half of the side of one side of the polygon, which corresponds to an angle of pi over n, because there are two pi angles in a circle. Now, if we use sine rules, we get that the sine of pi over n is equal to p over 2n over r. We can rearrange this and solve for p, which will end up getting p is equal to 2nr sine of pi over n. Now we can use Taylor expansions to get the following, where, as we notice, many of the other terms have n's on the bottom. And now all the terms with n in our limit as n go to infinity all go to 0. So we end up getting that the perimeter, aka as we go to infinity, the circumference of a circle is equal to 2 pi r. Now, in the case of hyperbolic geometry, we're going to have to make use of the following definition, where the sine of some capital angle A is equal to sinh A over sinh of C. In our case, we're going to again use the fact that our A is going to be pi over n, so our sinh of A is p over 2n, and our sinh of C is sinh of r. Now we can rearrange this equation again to solve for the side of sinh of p over 2n, and we end up with the following once we Taylor expand our sine term. And again, you can notice how all the terms with the over n will go to 0. And so we're left with p over 2n is equal to pi over n sinh of r. Now, if we multiply both sides by 2n, we get p is equal to 2 pi sinh of r, which is our new circumference of a circle in the hyperbolic plane.
Now that we've covered the math of hyperbolic geometry, let's go into some of its cool applications, starting first with hyperbolic geometry in space. We want to find the shape of the universe and possibly even predict our own fate. When scientists contemplate the geometry of our universe, two questions come to mind. Is the universe finite, and what is its shape? By examining the cosmic microwave background radiation, our universe appears to be homogeneous and isotropic. This is because the CMB is coming towards us from every direction with essentially constant temperature. From this information, we can hone in on three possible shapes of the universe which satisfy those two characteristics. These three shapes correspond to the exact three curvatures we mentioned above: a positive curvature corresponding to a spherical space, a zero curvature corresponding to Euclidean space, and a negative curvature corresponding to hyperbolic space. In his theory of general relativity, Einstein presented his field equations, which relate the matter in the universe to its geometry. Edward Hubble further specified this relationship in this equation, where h is the Hubble constant, g is the gravitational constant, rho is the density of the universe, and k is the curvature as before. Therefore, the curvature of the universe can be determined by measuring its density. From these measurements, astronomers have ruled out the case of k greater than 0, a spherical geometry for the universe, because the density of the cosmos is too low for space to arch back on itself in a spherical way. Thus, we are left with either Euclidean or hyperbolic geometries as possible shapes for our universe. Unfortunately, it is possible for both of these geometries to be either finite or infinite, so far we are unable to answer the question of whether space is finite.
An interesting idea is that if our universe is hyperbolic and finite, it could still appear infinite to us. As an article in Scientific American puts it, in a finite universe, we may be seeing the same set of galaxies repeated over and over again, Like a hall of mirrors, a finite universe gives the illusion of being infinite. The illusion would be shattered if we could identify repeated images of some easily recognizable object. The difficulty is finding objects that can be recognized at different times and at different orientations. It is difficult to imagine a finite hyperbolic space. A possible model is that of an octagon, whose opposite sides are paired so that when an object leaves one edge, it ends up on another. This is topologically equivalent to a two-holed pretzel, also known as a torus. Observers who live in the surface would also see an infinite octagonal grid of galaxies. Such a grid can be drawn only on a hyperbolic manifold, which is like this floppy surface where every point is a saddle point, as shown here on the bottom. All three of these geometries are equivalent topologically.
The shape of our universe will determine its ultimate fate. Let's consider the parameter omega, which is the ratio of the universe's actual density ρ to its critical density ρc. ρc describes the universe's density if its geometry is Euclidean. Now, if omega equals 1, we have a Euclidean geometry, which would mean that the universe will expand at a rate that approaches 0. If omega is less than 1, we have hyperbolic geometry. And the universe will expand infinitely, with matter becoming more and more spread out until we experience a big chill. Finally, if omega is greater than 1, we would have a spherical geometry. In this case, the universe would eventually collapse on itself in a big crunch. But we have ruled this option out. For now, the universe appears to have a hyperbolic geometry where the curvature is very close to 0. This could explain why, locally, space appears Euclidean to us.
The next application we're going to discuss is hyperbolic geometry as shown in nature. Using hyperbolic geometry as a tool for survival. Many examples of hyperbolic geometry occur in nature. Certain types of organisms tend towards hyperbolic geometry to maximize their surface area for survival. As r grows, the circumference of a circle in hyperbolic space becomes larger than the same circle with that same radius in a Euclidean space, as shown in this diagram. As we showed in our math section, the circumference of a Euclidean space is 2 pi r for a circle, while in a hyperbolic plane, it would be 2 pi sinh r. As we showed here on our graph, the circumference in a hyperbolic space is growing faster. Therefore, at a given same radius, a hyperbolic space circle would be larger than that of a Euclidean circle. In order to fit that same amount of matter into a Euclidean space, we often see things folding in on themselves, and often in nature we see this as a frilly crinkled sort of edge, and therefore we're able to fit more matter into a smaller space. Hilbert once said, if you try to fit negative curvature, like hyperbolic geometry, into a Euclidean space, you're forced to have boundaries, which is what we see here with the frilly organisms.
Here are some examples of organisms that exhibit hyperbolic geometries. This one is a nudibranch, a type of mollusk. Here we have a frilly flower, some lettuce, a cactus, and the folds of our human brain. Some scientists have related the amount of wrinkling of an animal's brain to its intelligence, as it provides more surface area and therefore more brain power. We also see hyperbolic geometry in corals. It's almost impossible for humans to construct accurate hyperbolic surfaces. But in 1997, mathematician Dana Tamina worked out how to model hyperbolic spaces using crochet. When hyperbolic lines are stitched onto these works, one can clearly see how the Euclidean parallel postulate fails to hold and how triangle angles add up to less than 180 degrees.
In 2005, sisters Margaret and Christine Wertheim began a project to crochet an entire coral reef. They hope to use the project to raise awareness of coral reef bleaching due to climate change. Furthermore, their project demonstrates how hyperbolic geometry is not as abstract or esoteric concept as it may seem. Margaret Wertheim is a science writer focusing on the physical sciences, and Christine is an art professor. Here is a short clip of Margaret explaining their coral reef project in a TED Talk.
In 1997, showed that you could crochet models in hyperbolic space. Here is this diagram in crochetness. And I've stitched Euclid's parallel postulate onto the surface, and the lines looked curved. But look, I can prove to you that they're straight, because I can take any one of these lines and I can fold along it, and it's a straight line. So here, in wool, through a domestic feminine art, is the proof that the most famous postulate in mathematics is wrong.
Our last application of hyperbolic geometry will focus on art. We'll talk about the Dutch graphic artist M.C. Escher, who explored hyperbolic geometry in his art. Escher was fascinated by the mathematical side of art and was well known for his tessellations. He created circle limit 1, circle limit 2, circle limit 3, and circle limit 4, each of which exhibits hyperbolic geometry.
Escher worked in the Poincare model of hyperbolic geometry. In this model, points represent points inside our Euclidean circle gamma. Lines represent either the diameters or open arcs. An incident with just means points that are incident with a line is the same way as we consider it in a Euclidean point of view. Now, in this view, we're reimagining hyperbolic plane onto this Euclidean two-dimensional circle. So the way we think about this circle is that as we get farther away from the center, we're getting infinitely more dense. So as we move outward, the geodesic gets longer. Thus, lines become curved to take advantage of the less dense center of the disk. The Poincare model, therefore, distorts hyperbolic space in the sense that straight lines appear curved as we get infinitely far away, approaching the boundary of the circle. Objects appear closer and closer together, though they are actually truly all equal. After looking into a textbook of hyperbolic geometry, Escher was introduced to the idea of keeping infinity in a finite space, as often used in models of hyperbolic geometry, such as that of the Poincare model. One way of depicting this concept is using tessellations. Tessellations are repetitions of equally spaced polygons such that they cover an entire surface. You can find these both in Euclidean and spherical, as well as in hyperbolic geometries. Regular tessellations consist of regular polygons and are characterized by the value pq, where p is the number of sides of the polygon used, and q represents the number of polygons that meet at a vertex. So in the case of this one depicted on the right, our p-value is 7 because we have a heptagon, and the q value is 3 as 3 heptagons meet at each vertex. As you can see in this picture, as we approach the edges, our heptagons are getting smaller and smaller. Therefore, it looks like it's reaching infinity. Now, this is that distortion we're speaking about, because in reality, in this model, they would all actually be the same size, and it would just look like an infinite chessboard of heptagons. Additionally, you can see that as we go far away, the lines on the heptagon seem to be appearing curved. That also is something we talked about earlier, but in reality, they really are straight, regular, congruent polygons.
Here is Escher's circle limit 4, which is a 6-4 tessellation. You can see how the angel and devil wingspans meet to form hexagons. At a given vertex, 4 hexagons meet. Notice how, to fit the tiles into a Euclidean picture of a circle, Escher had to shrink their apparent sizes as he moved away from the center of the disk. Here are Escher's other circle limits 1, 2, 3, and 4. Escher only made 4 works in the hyperbolic geometry because it's very laborious. He first made a lithography stamp of this tessellation pattern. Each piece consisted of a series of 20 printings. However, throughout his career, Escher created hundreds of Euclidean-inspired tessellations. Nowadays, with the help of a computer, we can easily transform his Euclidean tessellations into hyperbolic ones, as shown here and here.
For thousands of years, mathematicians have pondered proving and disproving Euclid's parallel postulate. At first, they just thought it was a corollary of the first four postulates, but over time they weren't able to prove that. And with much more time and many more burned manuscripts thanks to the bullyings of Gauss, we have reached the era of non-Euclidean geometry, which began to reveal strange and fascinating phenomena. We think what is truly the most interesting part is that some of the most simplistic creatures on Earth, like coral and sea slugs, have accomplished what mathematicians failed to do for so long: be models of hyperbolic geometry. We can never fully visualize the world of hyperbolic geometry, but in the little clues of frills of lettuce and the ponderings of the shape of our universe and its very fate, and in the creative liberties of Escher, we can begin to glimpse over this other world within our own.